I have to remind you that there would be no limit in the number of available threads per process. However, you're limited, uh, in reality, you're limited in the number of threads, depends on the type of memory you have, how much memory you have left. And some operating systems are limiting you on the number of processes you can have as well. As far as I'm concerned, for Windows 32-bit operating systems, the number of processes you can have, again, also is not theoretically limited. However, you're limited again to the amount of memory that you have. If you're speaking of other operating systems such as, let's say, embedded operating systems like Windows CE, I can tell you that you're limited to 32 processes. You cannot have more than 32 processes. And of course, on each process, again, you have unlimited threads, but again, you're limited to the amount of memory. So read the documentation for that particular operating system you're working with. I assume you're working with Windows 32-bit operating system, either Windows 2000 or Windows XP or even NT. But just in case if you're taking MFC courses and later on you're going towards embedded environment, you have to understand that you're limited to the number of processes over there. So now let's talk about the virtual memory system. Well, if you go back to a few years ago, actually a decade ago, back in 80s, 90s and so forth, as a programmer, you needed to preserve memory address space for your application. Why? Because you couldn't afford not to have that memory at runtime. You didn't want your application to fail. So what did you do? At the beginning of your application execution, what you said, you asked the operating system to pre-allocate chunk of memory for you. But you know what the problem was at the time? People were racing to get more memory without even using it. So application developers and companies became greedy. They didn't want them to fail, but they didn't care about other applications running at the same time. So the poor end user was failing. They couldn't run multiple applications at the same time. They had to close some application and launch the other application, and that was a problem. So what Microsoft, as one of the vendors of operating system, done for us is say, you know what, you don't have to preserve or pre-allocate memory. Not to mention that you still have the power in C++ to do so. Still you can do it, but as a Windows application developer, why should you be worried about the amount of memory that you need to pre-allocate? Microsoft says, you want it, I give it to you. As a matter of fact, you have up to 4 gigabytes of address space. Isn't that enough for you? So you never use them all. It's just a matter of Microsoft pre-allocate that much virtually. Not necessarily they allow you to have that much at runtime. They say you are entitled to getting up to 4 gigabytes of address space. But you're not going to have them all unless you really prove that you really need that much variable. Means go use it. Show me that you want to use it, I give it to you. But you are basically entitled of getting that much. So as you see on this screen, we have two types of memory in Windows operating system. We have physical memory and we have what? Virtual memory. Physical memory is how much you have RAM. And then virtual memory basically is a 4 gig address space, which is really 2 to the power of 32. And just because you have 32-bit operating system, they have given you 4 gigabytes of address space. So what's that anyways? As far as the 4 gigabytes address space goes, Microsoft depends on the operating system again, which I really don't want to get into the detail, but I bring up a couple of examples for you, divides that 4 gig address space differently. In the case of NT 4.0, just in case if you're designing for NT 4.0 operating system, what it does, it actually holds up to 2 gigabytes of address space for the operating system, 1 gigabyte for your DLLs, and 1 gigabyte to your application. In the case of Windows 2000, it actually breaks it into half. 2 gigabytes for the operating system, 2 gigabytes for the application. And then the upper portion of the operating system becomes your DLL shares. It really depends on the operating system level. It might be slightly different from one OS to the other. But in general, you get the 4 gig address space anyways. That's why you have seen in the market most applications that are running on NT 4.0 could run on 2000 or XP because they're very, very similar. But not necessarily 98 and NT or 2000 are, as compatible. So keep that in mind, just because of this virtual memory concept. So as I mentioned here, on the note also specifies, in Windows NT, an application may have up to 3 gigabytes of address space for its own use. So operating system shares 1 gig of its own with the application as well. But in 2000 it's not like that, or XP is not like that. So how does it work anyways? As we talked about, virtual systems, there are virtual addresses. That means 2 to the power of 32 combination of numbers, bits, right? That gives you 4 gigs of address space. However, by the time your application gets loaded, your application says, okay, I need, for example, I don't know, 1 meg of application at the moment. And I have up to 4 gigabytes, right? So what do? I start from perhaps 0 address, and I map that to my actual physical address. But your 0 not necessarily is 0 on physical. It might be mapped to another address on physical memory. What do you care? As long as you can have your own address space, you refer to that, and then operating system takes a look at your address and maps it to actual physical address. You're set. You don't have to be worried about it. Unless you want to do like device driver programming that you really need actual physical memory, there are some APIs that you can bypass the virtual memory. Shouldn't be any problem. But most of the time in Windows design, in the courses that I'm teaching at the moment, you never do that. You always go through virtual memory. Some operating systems do not have virtual memory at all. So keep that in mind. But see how virtual memory system works. When an application is started, the following process occurs. The first thing you do, you double click on the application, right? You're executing the application, and there you have your process. The process gets started. Remember, we mentioned that the process is an instance of a running application. So each process is assigned a 2 gigabyte virtual address space, not necessarily the physical memory. And then the virtual memory manager, which is a subsystem part of your operating system, what it does, it actually maps your virtual address space, which is a 2 gig address space, into the physical memory address. However, it takes a look at the application execution. If the application throughout the execution requires more memory, what it does, it takes a look at the physical memory. If there is available space, it maps more address. If it is not, it takes a look at inactive applications address space instead of the physical memory. Because if you think about it, at the same time, how many applications are running at the same time as an active application? If you think about it, only one. Only one window can be activated, right? So right at that fraction of the minute that you're working with application A, if other applications like B, C, and D are running, but you click on the window of application A, you're making that window to be activated. So basically that becomes a priority for operating system. You know what it does? Takes a look at the rest of the applications and sees no one uses them at that moment. Perhaps they are doing something in the background. That's a different story for that. But for the application you don't do anything with, operating system takes a look at the memory instead of the physical RAM and says these sections are not being used at the moment, but you need them. So what it does, it takes a snapshot of the memory, saves that portion of the memory into a file system. In Windows environment, they have different name. Page file.svs name is good for NT 4.0 or perhaps 2000. In Windows 9X or 9598, they know it as a swap file. Perhaps you have seen it before. So what are those files anyways? The file basically is your mapper. In other words, the 2 gig address space file that we're talking about is actually take the snapshot of the memory, saves it into a hard disk, and what it does, frees up the memory on the physical RAM for your active application. You needed more RAM, right? So uses that. By the time you click on an inactive application, what it does, it takes the inactive portion of the memory, might be another section or might be your application, to the hard drive and brings up the old application's saved state back into the memory. So that's why the hard disk starts flashing So sometimes, as you see, your machine, perhaps you have experiment that perhaps the more application you run, hard drive starts flashing more. So it becomes a little bit slower. That's why we say, hey, it's time to add more RAM, because the reason I'm, getting a lots of I/O in here just because I don't have enough memory. You can experiment that if you do have a very fancy graphical application, design, and then you don't have enough memory for that. You see hard drive really suffers. You really do a lots of flashing on it. So let's go through this step again. Then I have a video in which I'm going to show you. So number one, the operating system creates a new process. You get 2 gigs of address space. The virtual memory manager maps the application code into a location in the application's virtual address space. And then, of course, if your application uses any dynamic link libraries, the DLLs are also mapped into the process virtual address space. That's what we know as in process. If it's calling another exe which has its own address space, we call them out process. In other words, we are not bringing it into our own process. They have their own process. Then we have to do marshalling. And then, of course, a space for items such as data or stacks that are being set. And finally, application begins execution by using the addresses in its own virtual address. There's a note that says the application never directly accesses the physical memory. This is extremely important using the standard Windows-based application design. Again, if you want to do device driver programming, then you need to actually use APIs that allows you to directly access the physical memory. We don't talk about it right now. You have to take like CE courses or device driver courses that Apex Infotech offers, and then over there we talk about how to access physical memory directly. The virtual memory manager controls all access to physical memory through requests for access by using virtual addresses. There's an animation that you can actually launch it from your mastering series, which I would like to show it to you at the moment.